Framework for confidence intervals. Here's the issue. The true population mean is unknown or unobservable. Therefore, confidence interval is the range within which we expect the population mean to lie in with a given level of probability. Let's look at an example. Suppose that the analyst states that while no one knows what the average rate of inflation will be over the next 20 years, we are 90% confident that it will range between 1% and 3%. So do you see how this has all the elements of the issue that we just brought up? The analyst does not know precisely what inflation will be over the next 20 years. So the best she can do is she can construct a confidence interval within which she is 90% sure that inflation will be within over the next 20 years or so. And that's how we talk about uncertainty. So the framework for confidence interval is as follows. We start with our best estimate. It's called the point estimate. So what is your best estimate for population mean? Because remember, we don't know what the population mean is. So what is our best estimate? But then to construct a range, we need to go higher and lower than our best estimate. Now the next question is, how far above and below do you go? And that's called the reliability factor. And then what we do is we multiply the number of standard deviations that we need to go away from our point estimate by the value of that standard error. So let's expand upon all this. So as I said before, a point estimate is our best guess for what the population average will be, and that will be based on our sample average. So our sample average is our best estimate of what the true population average might be. For example, coming back to this inflation example, we don't know what inflation in the future will be. So our best estimate for future inflation will be what the historical average rate of inflation was over the last 20 years. Maybe that's our best estimate. But because it's just an estimate, we need to construct a sort of a range around that in order to account for the errors. So reliability factor is the number of standard errors required in order to construct the confidence interval. So the wider the goalposts you want around your estimate, the more standard errors we have to go on either side of our point estimate. Now this is where we have to decide whether we need to use Z distribution or T distribution, because based on which one we pick, it'll affect the number of standard errors we need to go on either side. So the decision rule is as follows. If the sample is large, we can use a Z distribution. On the other hand, if the sample is small and the underlying population is normally distributed and the population variance is known, then again we can use the Z distribution. In the third scenario, if the sample is small and the underlying population is normal, but the population variance is unknown, then we use a T distribution. So when do we use a T distribution? Look at all the signs. The sample is small. The population variance is unknown. That sounds like you're less certain. And that's precisely how an analyst chooses T. So if an analyst looks at a sample and he says that, you know what, this sample really is not that reliable because, you know, it's a small sample, there could be a lot of errors there, and we don't know too much about the underlying population, so therefore let's use T. Now, here's the thing, ladies and gentlemen. The thing with T distribution is we need tables. So on the exam, if you're going to be using T, they need to provide you with excerpts from the T table. On the other hand, with Z distribution, Z distribution has the following rules of thumbs, which we've seen from a previous module. So if you want 90% confidence around your estimate, you have to go up and down by 1.65 standard errors. If you want 95% confidence interval around your estimate, then you see how you got to widen your goalposts. Then you got to go plus or minus 1.96 standard errors on either side. And then finally, if you want 99% confidence interval, then the goalposts get even wider. You need to go plus or minus 2.57 standard errors on either side. And so there it is for t values. We do need the tables. And a word of caution here, even if the sample is large, in other words, it's reliable, you may still be asked to calculate t. Where does that fit in? Well, over here. Remember we said if the sample is large, you can use Z. Well, you know, large is relative. It's a judgment call, and you are not required to know what constitutes a large sample. But in practice, it's a judgment call. However, even if the sample is considered as large, the analyst, and in your case on the exam, you may still be asked to use a t distribution. But again, remember, the only way you can use a t distribution is if they give you excerpts from the table, because here it is. If I was using t and I wanted a 90% confidence interval, the goalpost would be something different than 1.65. So do you see why it's important to decide whether it's z or t? These are z numbers. So if you want t numbers for the same confidence interval, again, it'll be something different. In fact, it'll be higher than 1.65 because look at the connection. Because with t distribution, the sample is less reliable. So when the sample is less reliable, you want wider goalposts in order to account for the greater errors associated with your estimate. So do you see how there's a storyline behind the quants? Okay, and now, so the only other thing we need to do, ladies and gentlemen, if we can go back to our framework for confidence interval, we talked about point estimate, that's our sample. Reliability factor, that's when you have to decide whether we're using Z and T, because that tells you how many standard errors you need to go on either side. But then you need to tell me what the value is for each standard error, and that's the last step here. So in step 3, how do you find the standard error of the mean? And we saw this in a previous module. We just take the standard deviation of the sample and divide it by the square root of the sample size. That will give us the value for standard error.